On April 13th, 2026, in the city of Hangzhou in Zhejiang province, a Chinese automaker named Geely stood in front of the automotive world and announced that it had broken a record that the internal combustion engine's most sophisticated engineers, at Toyota, at Honda, at Nissan, at Mercedes-Benz, at BMW, had spent more than a century trying to claim for themselves. The record is called peak thermal efficiency. It measures the single most important number in the physics of any combustion engine, the percentage of energy contained in a given quantity of fuel that actually gets converted into usable mechanical power rather than being lost as waste heat through the exhaust, the coolant system, and the friction between hundreds of metal surfaces moving against each other, hundreds of thousands of times every hour. A higher percentage means the engine extracts more of what the fuel contains and wastes less of it as heat. It means more power from the same amount of fuel, more kilometers per liter, more miles per gallon, and lower emissions without requiring the engine to burn more cleanly, because it is burning more completely. For most of automotive history, the theoretical upper limit of what a mass-produced gasoline engine could achieve in peak thermal efficiency was treated by the industry as something in the low to mid-40s, a ceiling defined not by imagination, but by the physical laws governing how air and fuel mix, ignite, and expand inside a combustion chamber under the constraints of a production-viable manufacturing process. Geely's new IHEV engine achieved 48.41%. Guinness World Records independently verified the result, certifying not just the thermal efficiency figure, but also the fuel consumption number that followed from it. 2.22 liters per 100 kilometers, achieved in a certified highway fuel efficiency test around Hainan Island, delivering 106 miles per gallon under combined driving conditions. The previous record for a fuel-powered production vehicle in that test had been held by the Toyota Prius, which had managed 2.52 liters per 100 kilometers. Itself considered a remarkable achievement of Japanese hybrid engineering refined over more than 2 decades. Geely's engine consumed less fuel per 100 kilometers than the most fuel-efficient Toyota Prius configuration ever tested at that level, by enough margin that the comparison was not close. And Guinness did not simply hand out a certificate. The figure was tested, measured, verified against an international standard, and recorded as the official world record for a mass-produced combustion engine in a production road vehicle, not a prototype. Not an engineering concept, a car you can buy, rolling off a production line, entering the market in 2026. Before we go any further, I want to say something to you directly. The story we are about to build through this video is one of the most technically significant automotive stories in years, and it deserves to be understood with the full weight of the engineering behind it, rather than reduced to a headline number. This channel exists to give important stories exactly that treatment, sourced, precise, and honest about what the evidence actually says and what it does not say. If that is what you came here for, subscribe right now and turn on the notification bell. The automotive industry is changing faster right now than at any point since the invention of the automatic transmission, and I want you to be here for every chapter of it. To understand why 48.41% is as significant as it is, you need to understand where the rest of the industry has been sitting and how long they have been sitting there. The average gasoline engine in the average family car built anywhere in the world operates at a peak thermal efficiency of somewhere between 25 and 35%. That means for every 100 units of energy locked inside a tank of fuel, somewhere between 65 and 75 of them leave the car as heat, through the exhaust pipe, through the radiator, through the surface of the engine block, without ever pushing the car forward. This has been true for the internal combustion engine for most of its history, and engineers have known it and accepted it as the fundamental cost of burning hydrocarbon fuel in a piston chamber under real-world operating constraints. The energy loss is not negligence, it is physics. Combustion is inherently inefficient, and the pathway from chemical energy and fuel to mechanical rotation at the crankshaft passes through thermal and mechanical losses that cannot be eliminated entirely, only reduced. The engineers at Toyota understood this. In the early 1990s, when Toyota began the development work that would eventually produce the first Prius in 1997, their goal was to build a hybrid system that addressed the specific inefficiency of internal combustion by pairing the gasoline engine with an electric motor and a battery. The insight behind the hybrid concept was elegant and correct. Combustion engines waste the most energy at 2 specific moments. When the car is starting from a standstill because the engine has to overcome inertia without the torque advantage it has at higher speeds, and when the car is braking because all the kinetic energy accumulated during acceleration is dissipated as heat through the brake pads rather than recovered and reused. A hybrid system that uses an electric motor for low-speed starting, recaptures braking energy through regenerative charging, and allows the gasoline engine to operate only within its most efficient speed and load range could, in principle, dramatically reduce the total fuel consumption per journey, even without fundamentally changing the peak thermal efficiency of the engine itself. Toyota spent over 2 decades refining that concept into one of the most reliable and commercially successful powertrain architectures in automotive history. The dynamic force engines at the heart of Toyota's current hybrid lineup achieve peak thermal efficiencies of around 40% to 41%, a figure that the automotive press regularly describes as among the best in mass production, representing decades of refinement in combustion geometry, valve timing, and thermal management. Nissan, in developing the e-power system used in its Rogue hybrid and other vehicles, pushed the peak thermal efficiency of their dedicated hybrid engine to approximately 42%, specifically because their e-power architecture, like Geely's, allows the engine to operate as a generator running only at its most efficient operating point, rather than across the full range of speeds and loads that a direct drive combustion engine must handle. That 42% figure was celebrated in the automotive press and in engineering literature when it was announced, because jumping above 40% had taken most of the industry most of a decade to accomplish. The hierarchy before April 2026 looked something like this: conventional gasoline engines in the high 20s to mid-30s, best-in-class conventional hybrids including Toyota in the low 40s, and Nissan's dedicated hybrid engine architecture at approximately 42%, representing the outer edge of what mass production engineering had achieved with commercially available technology. Geely announced 48.41% and immediately entered production. The gap between 42 and 48 may sound modest, stated as raw numbers. In the context of combustion engine development history, it is not modest at all. Automotive engineers who study thermal efficiency will tell you that every percentage point above 40 requires disproportionate engineering effort because the gains become progressively harder to extract as you approach the physical limits set by thermodynamic laws. Moving from 42 to 48.41% required solving problems across multiple simultaneous dimensions of engine design, and understanding how Geely solved them is what makes this story genuinely worth spending time on. The core of Geely's breakthrough is an entirely reimagined combustion system they call Fire Tornado. The name is dramatic, but the engineering behind it is precise. At the center of it is a problem that combustion engineers call mixture preparation, the quality of the mixing between fuel and air inside the cylinder before ignition, which determines how completely the fuel burns and therefore how much of its energy is extracted rather than exhausted. Traditional fuel injection systems atomize fuel into droplets that mix with incoming air as the piston descends. The completeness of that mixing is a fundamental constraint on how efficiently the fuel subsequently burns. Geely's engineers used artificial intelligence to solve the fluid dynamics problem at a level of precision that was not available to Toyota or Nissan when they designed their current hybrid engines. Specifically, they applied AI large-scale computational models to increase the solution accuracy of the Navier-Stokes equations, the mathematical equations that govern all fluid dynamics, including the movement of air and fuel inside a combustion chamber, from the traditional 80% accuracy achievable with conventional computational methods to over 97%. With that dramatically improved mathematical model of what is actually happening inside the cylinder, their engineers could design combustion chamber geometry, intake port shape, and injector placement with a degree of precision that conventional computational fluid dynamics tools had not allowed. The results of that precision are visible in the engine's specific hardware parameters. The intake port uses what Geely calls a duckbill shape, an asymmetric geometry specifically designed to create a tumble flow pattern inside the cylinder that keeps the air-fuel mixture moving in a controlled vortex as it compresses, dramatically improving the uniformity of mixing. The stroke-to-bore ratio, the relationship between how far the piston travels and the diameter of the cylinder, is set at 1.39, a specific value selected to optimize the combustion chamber's surface-to-volume ratio at the moment of peak combustion, minimizing the heat lost through the cylinder walls. The compression ratio is 15.5 to 1, significantly higher than the 12 to 13 to 1 ratios used in most conventional hybrid engines, which means the fuel-air mixture is compressed to a much smaller volume before ignition, extracting more mechanical energy from the same combustion event. The fuel injection system operates at 500 bar of pressure, 500 atmospheres, which forces the fuel through injector nozzles so fine that it is atomized into micron-level molecular clusters, rather than the larger droplets produced by lower pressure systems, creating more uniform mixing with the incoming air and enabling more complete combustion. The ignition system uses 150 millijoules of ignition energy, a value that ensures reliable ignition of the highly compressed, finely atomized mixture even at the elevated compression ratios and lean fuel-air conditions that maximize efficiency. Then there is the friction reduction program, which Geely pursued with an intensity that reveals how seriously the engineering team understood that the gap between a 42% engine and a 48% engine was not going to be found in combustion chemistry alone. Inside the engine, there are 118 pairs of friction surfaces, Every pair of components in relative motion against each other, from the piston rings against the cylinder walls, to the journal bearings at the crankshaft, to the valve stems and their guides. Under operating conditions of 2,000 revolutions per minute, those surfaces experience up to 960,000 friction events per hour. Geely's engineers tested more than 200 rounds of component and system modifications, evaluated more than 70 different combinations of lubricating materials and surface coating formulas, and ultimately applied 11 separate friction reduction technologies simultaneously. Precision grinding and polishing of bearing surfaces to tolerances measured in nanometers. Diamond-like carbon coatings on the piston rings and other high-friction surfaces, a technology borrowed from aerospace and precision manufacturing, creating a surface so hard and so smooth that friction is reduced to levels not previously achievable in a production engine. Low-viscosity engine oil formulated specifically for this engine's operating temperatures and clearances. The combined result of the friction reduction program alone accounted for an increase in thermal efficiency of approximately 0.4 percentage points, a seemingly small number that, at the margin of what mass production combustion engineering can achieve, represents an enormous amount of engineering work precisely applied. I want to stop here for a moment and ask you to notice something about what you have just heard. The AI that helps solve the combustion fluid dynamics problem, the duckbill intake port that improves mixture formation, the 500 bar injection pressure that atomizes fuel to micron level, the diamond-like carbon coatings, and the 200 rounds of friction testing. None of these individual innovations are unprecedented in isolation. Researchers and engineers have studied each of them in laboratories and specialized applications for years. What Geely did was integrate all of them simultaneously, at a level of system-level optimization enabled by AI computational tools that were simply not available when Toyota designed the current Prius drivetrain, or when Nissan's engineers specified the thermal efficiency targets for the e-Power system. The scale of what just changed in the automotive industry's efficiency landscape is real, and it deserves the full attention of anyone who follows where technology is actually heading. If you are that person, subscribe to this channel and share this video with one person who thinks seriously about engineering and the automotive world. The comment section this video builds should be one of the most substantive discussions about combustion engine technology and hybrid strategy that YouTube has hosted. The IHEV system that surrounds this engine is as important as the engine itself, and understanding why requires stepping back from the peak efficiency number to look at how efficiency is achieved across an entire driving cycle rather than just at the engine's single best operating point. Every combustion engine has what engineers call an efficiency island, a specific range of engine speed and load at which it operates near its peak thermal efficiency. Outside that island, at lower speeds or partial loads or during acceleration, the same engine operates significantly less efficiently. Toyota's hybrid system improves efficiency in real-world driving by allowing the engine to operate closer to its efficiency island more often, shutting it off when the electric motor can handle the load, and restarting it when the load matches the engine's efficient range. Nissan's e-Power system takes this a step further by completely decoupling the engine from the wheels. The engine only ever runs as a generator, always at its optimal operating speed, never forced to respond directly to the driver's throttle input or the varying demands of road speed. Geely's IHEV uses a P1 plus P3 motor layout, a motor integrated at the engine crankshaft, and a motor at the rear of the transmission, that allows the system to function as a motor-led configuration rather than an engine-led one. Under WLTC standardized driving cycle conditions, the electric drive system is active in more than 80% of scenarios, meaning the engine is running less than 20% of the time during a standardized drive. And when it runs, it operates within its high efficiency zone rather than being forced across the full speed and load range. Engine operating time is reduced by over 27% compared to conventional hybrid architectures that remain engine-led with electric assistance. The electric drive motor delivers 230 kilowatts. Geely states this is 1.72 times the output of typical Japanese hybrid systems, which is sufficient to move the vehicle at speeds up to 66 kilometers per hour in pure electric mode without engaging the engine at all. The AI layer on top of this mechanical architecture is what Geely calls AI Cloud Power, built on what the company describes as Full Domain AI2, Zero, and a large model energy management platform. In practical terms, this means the system continuously reads external data, temperature, humidity, altitude, upcoming terrain from mapping data, and adjusts the petrol-electric energy split in real time based on what it predicts will be most efficient for the conditions ahead. The efficiency improvement Geely attributes to this AI management layer over conventional hybrid energy management systems is more than 10%. The vehicle's noise and vibration management is also AI-assisted. Engine stop position prediction algorithms anticipate where the engine crankshaft will be when shutdown is commanded, allowing the system to position the engine for a smoother restart, reducing startup vibration by 32.7%, compared to conventional hybrid systems that stop and restart the engine at whatever position it happens to be in. The result in a cabin is an experience noticeably quieter than equivalent hybrids, with cabin noise reported at only 1 decibel higher than the equivalent pure electric driving experience. The real-world fuel economy figures that emerge from this system have been verified by Guinness World Records under a specific test protocol. And it is important to be precise about what that verification covers and what it does not. The 2.22 liters per 100 kilometers figure, the 106 miles per gallon result, was achieved in a highway fuel efficiency test around Hainan Island, a route specifically chosen for its consistent conditions. The WLTC standardized fuel consumption for the Geely Preface I HEV, the sedan version of this system deployed in a full-size production vehicle under the internationally standardized driving cycle that covers urban, suburban, and highway conditions in proportion, is 3.98 liters per 100 kilometers, corresponding to approximately 59 miles per gallon. The Geely Manjaro I HEV, an SUV using the same system in a larger, heavier body, achieves 4.75 liters per 100 kilometers on the WLTC cycle, approximately 50 miles per gallon. These are the figures that a real owner driving a real car through a realistic mix of conditions should expect to approximate, not the 106 figure which represents the upper limit achievable under specifically optimized highway conditions. Both of these distinctions matter for an honest assessment, and both are in the script, because the people watching this video deserve precision rather than the version that sounds more impressive, but is less representative of what daily ownership actually delivers. Here is where the broader significance of this story extends well beyond one company's engineering achievement. The automotive industry spent the first half of the 2020s in an extended debate about whether the future of personal transportation was electric vehicles, plug-in hybrids, or full hybrids, and in that debate, the internal combustion engine itself was frequently written off as a technology in managed decline, something to be phased out rather than further developed, a legacy system waiting to be replaced rather than a platform still capable of meaningful advancement. What Geely's IHEV system demonstrates, certified by an independent third party at a level of efficiency that no Japanese hybrid manufacturer has publicly matched, is that this assumption was premature. The combustion engine, paired with intelligent hybrid management, when developed using AI-assisted combustion modeling at a precision level that was not available even 5 years ago, still has a frontier to push. And for the billions of people around the world who live in countries without the charging infrastructure to make battery electric vehicles a practical daily reality, that frontier matters enormously. Geely is not alone in recognizing this. Toyota sold approximately 4.4 million hybrid vehicles in 2025, accounting for roughly 42% of its total global volume, indicating that the market for non-plug-in hybrids remains enormous and growing. Chery and Changan, two other major Chinese automakers, are simultaneously expanding their own hybrid engine programs, with some targeting fuel consumption figures of 2 to 3 liters per 100 kilometers under certain conditions, parameters that would have described a record-setting achievement rather than a competitive baseline just a few years ago. The Nikkei has reported that Chinese automakers are not just surpassing Japan in electric vehicle technology, but in traditional powertrain engineering as well, a conclusion that Geely's 48.41% Guinness record provides the most concentrated evidence for. The companies that have dominated the efficiency conversation in combustion and hybrid engineering for 3 decades, Toyota, Honda, Nissan, now face a Chinese counterpart that has moved past their best published figures and immediately entered production at scale. The honest caveat this video requires is the one that any rigorous treatment of a new technology's launch numbers always requires. Geely's 48.41% thermal efficiency figure is a certified peak value, measured at the specific engine operating point where the combustion system performs best. The average thermal efficiency across all operating conditions, which is what determines fuel consumption across a realistic driving cycle, is lower. The WLTC figures of 59 miles per gallon for the Preface and 50 miles per gallon for the Manjaro reflect that real-world average. Geely is a large and credible automaker, and the Guinness certification provides meaningful independent verification of the headline figure. But verification of a peak bench test result is different from the long-term real-world reliability data that builds the kind of reputation Toyota's hybrid systems have earned over 25 years of consumer ownership. The vehicles deploying this system are entering production now, which means the real-world durability evidence that would place this achievement beyond any remaining question has not yet accumulated. The engineering specifications and the certified test results are real. What remains to be confirmed across millions of operating hours and millions of owners' hands is whether the precision engineering required to achieve this level of efficiency maintains its performance as components wear and as the AI calibrations encounter the full variety of real-world conditions across hot summers and cold winters and dusty roads and urban stop-start traffic that no laboratory test protocol fully captures. These are the honest limits of what the evidence currently supports. They do not diminish the significance of what Geely announced on April 13, 2026. They contextualize it, which is what every serious analysis of a technology breakthrough owes to the people who are trying to understand what it actually means. What it means, fairly stated, is this. A Chinese automaker working with AI-assisted combustion modeling tools that gave its engineers access to fluid dynamic solutions at a level of accuracy not previously available in automotive engineering, combined those computational advantages with 500 bar injection pressure, 15.5 to 1 compression, diamond-like carbon friction coatings, Miller cycle valve timing, and an AI-driven hybrid energy management system that runs on electricity more than 80% of the time, and produced an engine that Guinness has certified as the most thermally efficient mass-produced combustion engine in the history of the automobile. It went immediately into production. It will be deployed across multiple mainstream Geely models in 2026, and it approaches, from below, the 50% thermal efficiency that Formula One power units achieve, using the absolute cutting edge of motorsport engineering, technology that costs tens of millions of dollars per unit and is designed to survive for a few hundred kilometers of race use, not hundreds of thousands of kilometers in a family sedan. The internal combustion engine has been declared dead many times in the past decade. On April 13, 2026, in Hangzhou, it published a number that suggested it had other plans. If you stayed with this video through the combustion physics and the Navier-Stokes equations and the diamond-like carbon coatings, I want to thank you directly. That is exactly the level of engagement this channel was built for. So here's the question I want you to take into the comments below, and I want your most considered answer rather than your fastest one. Geely's achievement suggests that the combustion engine, paired with AI-optimized hybrid management, still has meaningful efficiency gains ahead of it. Does that change your view of the timeline for full electric vehicle dominance? And do you think the rest of the automotive industry, particularly Toyota and Honda, will be able to match or exceed 48% thermal efficiency in mass production within the next 5 years? One position. Your clearest reasoning. Let us build a comment section that actually engages with the engineering question this video just raised. Subscribe to this channel, turn on the notification bell, and share this video with one person who thinks carefully about technology and where the automotive world is actually heading. I will see you in the next one.